It's not only fish grown in the Negev desert, but all sorts of vegetables, including this red pepper.
In 1973, deep beneath the Negev desert, a routine geological operation was taking place that no one expected would change how people think about deserts forever. A drilling team, led by geologist Eliezer Issar, was conducting standard underground surveys, analyzing rock formations and mapping geological layers far below the surface. Everything about the mission suggested predictability. The expectation was simple: dry rock, dense sandstone, and nothing more than data to bring back. But as the drill pushed deeper, passing layer after layer of compressed stone, something unexpected happened at around 2,300 feet underground. Instead of resistance or empty rock cavities, the equipment suddenly broke through into a pressurized system. Within seconds, water erupted upward with enough force that it didn't require any mechanical pumping to rise. It surged naturally, driven by thousands of years of trapped underground pressure. This wasn't a shallow groundwater pocket. It was something far larger and far older than anything the team had anticipated. What they had accidentally tapped into was later identified as part of the Nubian Aquifer, a massive underground water system spanning multiple countries and containing water that had been locked away since ancient climatic eras. At that moment, none of the team fully understood the scale of what had just happened. They only knew that a desert drilling operation had unexpectedly
As the initial excitement settled, the reality of the discovery began to reveal itself, and it was far more complex than anyone expected. The water flowing from the aquifer was not ordinary groundwater. It had been isolated for tens of thousands of years, trapped in porous sandstone formations since a time when the Sahara was not a desert, but a green, living landscape. Over that immense period, the water had slowly absorbed minerals from surrounding rock layers, creating a composition that was chemically very different from surface freshwater. Even more striking was its temperature. After being stored deep within the Earth's crust for millennia, geothermal conditions had gradually heated it to nearly 99 to 104 degrees Fahrenheit, roughly equivalent to human body temperature. While it was technically water, it was far from suitable for conventional agricultural use. Early tests quickly confirmed the problem. When introduced into crop fields, the water caused rapid stress in plants. Growth slowed almost immediately. Leaves began to discolor, and within days, the damage became visible on a wide scale. Within 2 weeks, most test crops had failed entirely. The combination of heat and mineral content made it hostile to traditional agriculture systems. At this point, the logical conclusion was straightforward. Despite its abundance, the water seemed unusable for anything practical. But instead of abandoning it entirely, researchers began to reconsider the problem from a completely different angle, questioning not what could be fixed, but what could naturally exist within these extreme conditions. Rather than forcing conventional agriculture to adapt to conditions it clearly could not tolerate, researchers shifted their perspective entirely. Instead of asking how to make crops survive in this environment, they began asking a more fundamental question. What type of life is already adapted to fluctuating salt levels, warm water, and mineral-rich environments? This shift led them away from plants and toward aquatic species that had evolved under similar stress conditions. 3 fish species quickly stood out as potential candidates. The first was barramundi, a fish known for its ability to thrive in brackish environments where freshwater and seawater naturally mix, constantly adjusting to shifting salinity without biological stress. The second was tilapia, one of the most resilient farmable fish species in the world, capable of surviving in highly variable water conditions that would be fatal to most aquatic life. The third was European sea bass, a migratory species that naturally transitions between freshwater and marine ecosystems throughout its life cycle. What made these species especially interesting was not just their tolerance, but their biological flexibility. They were already built to handle unstable environments. On top of that, the temperature of the aquifer water, once considered a disadvantage, now became an unexpected advantage, aligning closely with the natural thermal preferences of tropical fish. Slowly, the problem began to transform from an unusable water source into a potential.
By the early 2000s, the theoretical idea had evolved into a real-world experiment. In the Negev desert, large-scale aquaculture facilities began to take shape in locations such as Kibbutz Mashabe Sadeh and Arava Tech fisheries. These were not small test setups. Entire landscapes were reshaped to support engineered ponds, controlled water channels, and integrated aquaculture systems designed to harness the underground aquifer. Water was continuously pumped from deep beneath the desert floor, filling vast containment ponds where fish species like barramundi, tilapia, and sea bass were introduced. At first, the conditions appeared almost too ideal. The fish adapted quickly, showing minimal stress and rapid growth rates, as if the environment had been unintentionally tailored for them. Within months, the system began producing measurable yields, and over time, it scaled into thousands of tons of fish annually. What made this development particularly significant was not just survival, but efficiency. The fish were thriving in a system powered by geothermal water that required no external heating. Energy costs that would normally make tropical aquaculture expensive in colder regions were completely eliminated. On paper, the project appeared to be a breakthrough in desert agriculture. However, as production increased and systems became more complex, an underlying issue began to emerge.
As the aquaculture system expanded, a hidden problem began to surface, one that is unavoidable in any high-density fish farming operation. Fish continuously produce waste, and in a closed environment, that waste does not simply disappear. It accumulates in the water, breaking down into ammonia, a compound that is highly toxic to aquatic life. At low concentrations, ammonia begins to damage fish gills and weaken their immune systems. As it continues to build, it triggers a chain reaction in the water, where bacteria convert it first into nitrites and then into nitrates, each stage still harmful in high amounts. Over time, the system begins to turn against itself. The very environment that sustains the fish starts to become toxic to them. In most commercial fish farms around the world, this problem is managed using filtration systems, bioreactors, and continuous water treatment processes. However, these solutions require significant energy input and operational costs, often consuming massive amounts of electricity just to keep the water stable. Another common solution? The turning point came when researchers began to re-examine what the fish waste actually represented. What initially appeared to be a dangerous byproduct turned out to have an entirely different identity when viewed through a different lens. Ammonia, while toxic to fish, is chemically rich in nitrogen, one of the most essential nutrients required for plant growth. In conventional agriculture, nitrogen is produced through industrial processes, like the Haber-Bosch method, a highly energy-intensive system responsible for a significant portion of global energy consumption. Suddenly, what had been classified as waste was redefined as a valuable agricultural input. This realization led to the development of a closed-loop system, where fish farms and agriculture were no longer separate operations, but interconnected components of a single cycle. Water from the fish ponds, now enriched with organic nutrients, was directed into agricultural fields, where crops such as olive trees and date palms absorbed the nitrogen naturally. The soil acted as a biological filter, breaking down compounds gradually while allowing plants to draw in nutrients over time. The results were immediate and surprising. Crop yields increased by 15 to 20% in some test areas, and plant health improved noticeably compared to traditional fertilizer-based systems. Even more unexpected was the role of salt. Instead of damaging crops, the moderate salinity of the water triggered adaptive stress responses in certain plants, enhancing flavor and concentration in fruits. What had begun as a waste management problem had transformed into a self-sustaining agricultural enhancement system, where nothing was discarded and everything contributed to the next stage of production.
As the system matured, its economic structure revealed why it was so powerful. Water, typically one of the most expensive inputs in desert agriculture, became dramatically cheaper due to the naturally pressurized aquifer. Instead of relying on energy-intensive desalination or freshwater transport, the system used brackish underground water that required minimal processing. This alone reduced operational costs significantly. On top of that, fish waste eliminated the need for synthetic fertilizers, which are normally produced through energy-heavy industrial processes. Together, these two factors created a dual industry system where fish farming and agriculture supported each other financially and operationally. The fish provided nutrient-rich water, while crops purified and reused it, forming a continuous cycle with almost no external waste. Economically, this meant that
two traditionally resource-intensive industries were now sharing infrastructure and reducing each other's costs instead of competing for resources. The impact extended beyond efficiency. The system also had environmental benefits, including reduced carbon emissions due to the elimination of fertilizer production and heating requirements. In some cases, it even became carbon negative due to plant absorption and reduced industrial activity. As this model proved successful, other arid regions began exploring similar systems, recognizing its potential for deserts worldwide. What began as a local experiment in Israel gradually evolved into a scalable agricultural model with global implications, especially for regions facing increasing water scarcity.
Ultimately, the Negev system demonstrated a fundamental shift in how environments are understood and utilized. What was once considered a barren and hostile desert turned out to be a highly specialized ecosystem, capable of supporting productivity when approached correctly. Every challenge that initially appeared to make the region unsuitable for agriculture, heat, salinity, mineral content, and isolation, became an advantage once the system was designed around them instead of against them. The aquifer provided stable water and geothermal energy. The salinity supported resilient crops. The fish waste provided natural fertilizer. And the desert climate reduced disease pressure common in humid agricultural regions. Instead of forcing nature to conform to human expectations, the system adapted human methods to align with natural conditions. This shift in perspective is what made the entire model successful. It was not about overcoming limitations, but about recognizing hidden functionality within them. As climate change expands arid regions globally and freshwater resources become increasingly strained, the Negev model offers a powerful example of how reframing constraints can unlock entirely new systems of productivity. The deeper lesson is not about fish or water alone, but about perception itself.